Welcome back. This will be lecture 24 of EC253C. We have been discussing about the timers. In last two lectures, we discussed what timers are and what are the steps to program a timer. There has been a long gap between the last lecture and this one due to some technical glitches. So I suggested that before watching this lecture, you should once again go through the previous two lectures, lecture 22nd and 23rd, because in those two lectures we discussed about the programs and today about the timers, and today we are actually doing some examples on timers. In last lecture, we discussed what are the steps to program a timer. A basic timer, the basic steps to programming a timer are given here. The first step is to load the timer counter register with a value. That value depends upon the time delay we want. In an 8-bit timer, we can load any value between 0 and 255. Lower the value, more the time delay, because more time the timer will take to reach the final value, that's 255, and overflow. We will later see how to calculate the exact value to be loaded in the time counter register. After loading the timer counter register with any value, we start the timers and also configure them in which mode we have to use them. So we have two control registers, TCCR0A for each of the timers, TCCR0B. We have discussed previously that TCC in our operations, in the modes we will be discussing in this course, will always be loading timer control register A with 00, and timer control register B, it will also give us the mode whether we want to use timers as timers or as counters or other modes, and also this will determine the prescaler, whether we want to run timers at a frequency that is equal to the frequency of the crystal attached to the microcontroller or at some other frequency. That is the prescaler. That will also be determined by the value that we load into the timer control register B. If we don't want any prescaler and we want to run timer 0 in normal mode, we will load TCCR0B with 00000001. On a hex we can write 0x01. When we load the timer control register B with this value, the timer will start incrementing. The timer will basically start and it will count whatever value we have loaded in timer counter register. It will start incrementing and subsequently it will reach 255 and then overflow. Whenever it will overflow, the timer overflow flag will be set. So we will, after starting the timer in step 2, we will keep monitoring timer overflow flag. Once the timer overflow flag is set, that means timer has reached to 255 and overflown. We will stop the timer by loading timer control register B with 00, and then we will also clear the timer overflow flag so that we may use it again. So these are the steps, the basic 5 steps we use in a timer. So today we'll be discussing about a program, an example where we can use the timer. A simple example, it's example 9.3 of your textbook. We have to generate a square wave on any of the pins, maybe port B, pin 5. So we have to generate a square wave on port B, pin 5, port B.5. A square wave is nothing, it's something like this. We will have 1, 0, and this waveform will repeat itself. So basically, if we have an LED connected to port B.5, when an LED connected, it will blink. It will generate a square wave on the port B.5 and we have an LED connected to it. The LED will obviously blink. Before discussing the program, you should know there are two main characteristics of a square wave. One is the time period, time after which the wave repeats itself. That's actually time period. It's equal to the on time, t on, plus t off. Or we can also call it frequency, because frequency is just the inverse of the time period, number of cycles per second. So this is the one thing, that frequency or the time period of a square wave. Then there is another thing, duty cycle. Duty cycle we usually represent in percents. The duty cycle is actually the time it is on, t on, divided by the total time period. That's t on plus t off. That means it's actually the portion of the time period for which the signal is high. For example, in this, if we consider that t on and t off is equal, then the duty cycle will be 50%, because t on plus, since t off equal to t on, duty cycle will be t on divided by t on plus t off, but t off is equal to t on, so we can write t on, that means 0.5 into 100%, that is 50%. But if we have a wave like this, for example, it's on for 1 second and off for 3 seconds, so the time period again will be equal to 4 seconds. But here the duty cycle equal to 1 divided by total time period 4, that's only 0.25, that's 25%. That means the signal is high only for 25% of the time. In this case, it's not mentioned that what is the time period of the wave and what is the duty cycle, so we can take any value. So what are the steps? These are our 5 steps, but before that you should know that if we have already discussed that if we want to use a subroutine in our program, we need to initialize the RAM. And how do we initialize the RAM? We actually need to put some values in stack pointer high and stack pointer low, because stack pointer is a register that always points to the top of the stack, and it's a 16-bit register. The integer registers are mentioned or referred like stack pointer low and stack pointer high. So first we need the last value of the RAM, so that we start the last with the last value. We have discussed this thing in our previous class. So how do we initialize the RAM first? I will get the RAM end, that's the last location of the RAM first. That I get using a command RAM end, and load into any of the general purpose registers. R20, in R20 I will the higher byte of the address of the RAM end, and in another register I will load the lower byte of the last location of the RAM. I have already explained this thing. And then I will put the higher byte in SPH and lower byte in SPL. That I will do using out command, out SPH. Where is the high byte? In R20. SPL R21. This is a standard thing we do in every program in which we use subroutines. Fine. After this, since we need to generate a square wave on port B pin 5, we need to configure it as output port. How do we configure it as output port? By writing 1 So in DDRB register, so I can write set bit immediate DDRB, the 5th pin, comma 5. Okay, and then I need to send high to this port B pin 5, and then after some time low. So I can simply write set bit 5th pin of port, then call delay, and after delay I will complement this pin because it was high, now it will be low, or I will clear, simply clear CBI port B5. Then I will again call this delay, and then I will again set the bit because now I again have to send 1 to it. So I will jump back, relay to jump, or a simple jump to a location ABC. ABC will be here. So this is the program. We have done it we have done it earlier also. We had an LED to a particular pin, and we blinked that LED. This is the same thing. We are now generating a square wave. We are turning it on, sending high to that pin, and then calling some delay, and then sending low, again calling some delay, and repeating this process. It's as simple as it is. Okay, now the problem is defining this delay function. Previously we used to define this using NOPs and other things, but this time we will actually define the delay using our timers. So far it's good. We have already done these things in our previous classes. Now the different thing is that the delay this time will be defined using timers. So how will define delay using timers, or generate delay using timers? The first step is to load a value in the counter register. If we had known how much delay we need, for how much time we need to keep it on, we would have put a particular value in timer counter register. But this time the time period of this wave is not mentioned, so we can put any random number between 0 and 255, basically between 0 and FF. So that I do by loading some value LDI in R20 again, or maybe in some other general purpose register but greater than 20, any value, for example 0 cross F0. And this value, the first step actually is in the timers to load the timer counter register with some value. So I will load this value now in the timer counter register. That I will do using the out command, out tcnt0 R20. So my first step is done. The first step here, load a value in the timer counter register. This is done. I have loaded a value in the timer counter register, of course randomly, because no time delay was mentioned. If the time delay had been mentioned, I would have calculated the exact value that I needed to load in the timer counter register. After this, I need to load 00 into timer control register A and 01 in timer control register B. I will again do. You should remember that we don't directly load values into the timer control register or any input output register, any special function register. We load the values in general purpose registers first, and then transfer it to the input output registers. So again I will load R20 with some value that is 00 and put it into timer control register TCCR0A R20. After that I will load the time. I have to load now timer control register B. For that I will load 20 with 001. Why 01? Because I want it to run in the normal mode with no prescaler. I want my timer to run in the normal mode with no prescaler R20 0x01. Now I will put in timer control register B. The moment I put it into timer control register B, my timer will start running. That means since in my timer counter register I had loaded F0, F0 after a certain time period will become F1, then F2, then F3, then F4, and finally FF, and then it will overflow to 00. And this time period, the time it will take to increment, is actually equal to the frequency of the crystal attached to the microcontroller, because we have used no prescaler. So now I have to monitor whenever there will be a jump from FF to 00 that the timer will overflow. The timer overflow flag will be set. And I have also previously discussed that a timer overflow flag is actually part of TIFR0 register. So I will keep on monitoring this bit of this register, whether it is set or not. So I can simply write command. We have also discussed, I think we have discussed this command in our jumps. Skip bit if bit if set. That means if this particular bit is set, skip if bit is set, skip if bit is set, skip if bit is set. That means I need to skip something. If the bit after this register, after this command is set, what's the bit here? Timer overflow. That I will write TI, because I need to mention the register TIFR0, timer overflow bit of that TIFR0 register. And skip, what I will skip? The next instruction. For example, there will be an instruction, and if this bit will be set, the next instruction will be skipped. And if this bit will not be set, when will be this bit set? When there will be an overflow. So normally this bit will not set until there is an overflow. So normally the instruction after it should not be skipped. We should be in this loop. We should be here always. We should not execute the instruction after it until the bit is set, because we have to wait for this time period, for which we have to keep it high. So the next instruction I can write simply to jump back RJMP to XYZ. Now look, the normally timer overflow flag is not set. It is not set. That means when this instruction is executed, it says skip if bit is set. Skip the next instruction, the next immediate instruction if bit is set, but bit is not set, so it won't skip. The programmer, the controller will not skip the next instruction, so it will execute the next instruction and it will again jump here. So it will again check if the bit is set. If the bit is set, it will skip this instruction, but if bit is not set, it won't skip this instruction, but will execute this instruction and it will jump back to this XYZ, and this instruction will keep on executing until bit is set. Once the bit is set, that means I have reached my intended delay. Now I need to switch pin 5 of port B to 0. So at that time, when the timer overflow flag is set, the next instruction, only one instruction immediately after this will be skipped. That means this instruction will be skipped, and the instruction, so that it won't jump back, but the next instruction will be executed. What will be the next instructions? I have to restart the timer, and before restarting the timer, I need to clear timer overflow flag. So first I can clear the timer overflow flag. LDI R20. I need to clear timer overflow flag, and I have mentioned this point that we clear timer overflow flags by writing 1 to them. So I can simply write set bit immediate timer overflow flag of TIFR0 TIFR0 TOV, and then I will restart the timer. So how I will restart the timer? First I will stop the timer. So first I have to stop the timer. That means I will put 00 in timer control register B. That I will do by loading any general purpose register with 00 and then putting that value in timer control register B, and after that I will simply clear also the timer overflow flag so that this timer will be used once again. TIFR0 timer overflow flag, and I will return to the original program. I will return to the original program here, clear the bit, that means it will go 0 now. It was 1, that end will go 0. Then again call the time delay, the same time delay. That means T on will be equal to T off. I will get a square wave. I will once again go through what we discussed here. We needed to generate a square wave of any time period, any duty cycle, a random time period and a random duty cycle. What we did, first we initialized the stack, these 4 instructions, sorry. Stack initialization was necessary because we were using a subroutine. Whenever we use a subroutine, we need to initialize the stack, and we have discussed how to initialize the stack. I write the commands here. After that, since we were using port B and pin 5 of port B, I had to configure that port as output port. That I did by setting the bit, which bit 5 of DDR-B register. Okay, that's also fine. After that, what I did, in fact, these 5 lines, I am setting the bit in consideration, that's the port B pin 5 as high. That means I am sending a high on port B 0.5 and then calling some delay. It will be high for some delay. Then I am clearing it, that means it will be 0. Again calling the same delay, it will be 0 for some time. Then I am repeating these steps, that means it will be 1 again, 0 again, 1 again, 0 again, and I will have a square wave. Now the question was how to generate this time delay. The time delay I am calling here, I am defining this subroutine here. Previously we had used NOP operations to actually implement time delays, but this time we are using timers. And how do we do that? The basic 5 steps we will be doing. First, I will be loading timer counter register with some value. That value will actually depend upon the time delay we need. But since here we don't have a set time period, I will be loading any random value in my timer counter register. So I am loading a value F0 in my timer counter register using these 2 commands. After this, I am configuring my timer and also starting it, configuring in normal mode with no prescaler and as a timer, and also starting it. So for that I set a value in timer control registers. Timer control register A, I put a value 00 in it, and I put a value 01 in timer control register B, so that timer starts and timer starts counting. Whenever this instruction will be executed, my timer will start counting from F0 to F1, F2, F3 up to FF, and subsequently will overflow, so that I keep on monitoring the timer overflow flag. That's actually part of this register, TIFR0 register. So I keep on monitoring. If the bit is set, I will skip this instruction, that is jumping back, and execute these instructions. But until the bit is not set, that bit is cleared, I will keep on jumping back and checking again, so that I will actually wait until the bit is set. That means the timer is overflowed. That means the required time delay has been achieved. Once that is done, what I will do, I will stop the timer. That I do by loading 00 in timer control register B, because I start the timer by loading 01 in timer control register B. Whenever I have to stop the timer, I have to load 00 in timer control register B. And then I also cleared timer overflow flag. That I do, I have all previously mentioned that this thing, that we clear timer or only the timer overflow flags by setting a 1 or by writing a 1 to them. I clear them so that they may be used in future, because we will be calling this delay function again and again. And then I return to the main program. That's it. That are the steps. Now the question is, how much time delay calculations, how much time delay did we get using this program, delay calculations. For that will be actually depend upon the crystal frequency we have used, and also that will depend upon the prescaler. Two things. Since we are using no prescaler in this example, therefore the delay will be depend upon the crystal frequency. Let's assume we have used a 16 megahertz crystal. That's most commonly used in Atmega 328 microcontroller, 16 megahertz. Since we have used a 16 megahertz crystal, what will the time period of the crystal? It will be 1 by 16 megahertz, that means to 10 raised power 6, that means 10 raised to minus 6. That comes out to 0.0625, 10 raised to minus 6 will give me microseconds. So also the time period of the timer, that means the rate of the timer on which it will click, it will increment, will also be equal to 0. Because we have not used any prescaler, 0.0625 microseconds. Now how many clicks does it need before overflowing? That will depend upon the value we have loaded in the timer counter register. In this case we have loaded a value F0, so it will become, after one time period, that means after 0.0625 microseconds, it will become F1. After another 0.0625 microseconds, it will become F2. And similarly, after few microseconds, after another 0.062 microseconds, it will become F3. And at some time, it will reach to FF, then overflow. So how many steps this will be? These will be actually FF minus F0 steps. FF is 255. This F0, this will actually give us F steps, that is 16 steps. Plus 1 step of overflowing. We need 16 steps from F0 to FF, F0 to F1, F2, F3, F4, F5, F6, F7, F8, F9, FA, FB, FC, FD, FE, FF. 16 steps. FF minus F0, because it's 255. And F0 will be 255 minus 16 will be 239 perhaps. Yes, 239 F0. That is 16 steps. Plus it will take another step to overflow actually from FF and 00, because you should note that the timer overflow flag will not be set when the timer counter register reaches to FF. It will be set when the timer counter register overflows from FF to 00. So total there will be 16 plus 1 steps. That means the total number of steps will be FF minus the initial value we have loaded in the timer counter register, that is F0, or any other value. If we had used any other value, that would have been any other value, plus 1. In this case, that's 17 steps. Each step takes 0.0625 microseconds. So total time delay will be 17 into 0.0625 microseconds. That comes out to be 1.0625 microseconds. So in this example, we'll be getting a time delay of 1.0625 microseconds. That means my square wave will be on for 1.0625 microseconds and it will be off again for 0.0625 microseconds. What is the time period of this square wave then? 1 plus 0 t on plus t off. That will come to 2.125 microseconds. This is a time delay, and frequency will be 1 divided by this time delay. I hope that is clear. So now the question is, what will be the maximum time delay we can generate? Maximum time delay. Lower the value in timer counter register, greater it will take to reach FF and subsequently overflow. What will the maximum? What's the minimum value that we can load in the timer counter register? That is 00. And then it will become 01, 02, 03 up to FF, and it will be 255 increments plus 1 of the overflowing, and each increment takes 0.0625 microseconds, as we have discussed earlier here. So the highest time delay we can generate will be equal to 255 plus 1 multiplied by 0.0625. That 256 into 0.625, that's 16 microseconds. What if we need, for example, a time delay that's greater than 16 microseconds? What if we need a time delay of 160 microseconds? What we do? Here we use Prescalers, so that the incrementing frequency, the time period of the increment of the timer, is not equal to the crystal frequency, but it's actually the fraction of that. In fact, we slow our timers so that we can get more time delays. Also, we can get more time delays by using timer 1. Because you must remember that timer 1, unlike timer 0 and timer 2, is a 16-bit timer. That means it counts from 0 to FF. That means we can get a time delay of FF plus 1 into 0.0625. That's very huge. But if we have to use timer 0 and get a time delay that's larger than 16 microseconds, we use Prescalers. We'll be discussing these Prescalers and other things in our next lecture. Thank you.